All right, so this is going to be the screencast for doing or drawing Lewis structures for molecules as well as polyatomic ions. So here's your essential question. How many valence electrons do all atoms except for hydrogen and helium need in order to be satisfied? And then why? So by the end of this today, hopefully you will be able to take what we know about valence electrons and Lewis dot structures and put them together, put all of that information together to form the Lewis dot structures for an actual molecule. So there's some steps to this, and you're going to see this throughout, that I'm going to take you through the steps, and then I'm going to have you do some practice problems. So the first step is, for the Lewis structure guidelines, is you're going to use the chemical symbols for the various elements to write the skeletal structure. So you're just going to get a basic skeletal structure just with a single bond between all of the atoms involved. Well, how do you figure out which order they go in or what bonds to what? That's where we're going to have to use our electronegativity values. The least electronegative atom is the one that goes in the central position. So if you use your table of electronegativities, you can tell which one has the lowest value. That goes in the center. A few other rules with this: hydrogen always occupies the terminal position, so hydrogen is always going to be on the outside. And the halogens are always going to occupy the outside positions except when a more electronegative element is present. So if something is more electronegative than a halogen, which would only be really another halogen, you still will put the least electronegative element in the middle. Carbon often forms chains. So when you think about like fats or carbohydrates, like if I take glucose and string it together, which is just going to be a whole bunch of carbons bonded together, those carbon rings, I can make a starch, or in a lipid, which is going to be the chains of fatty acids, so lots of carbons bonded to each other. So you can have multiple carbons kind of in the center of an atom, or in the center of that compound. You might see some examples of those. So that's the first rule. The second kind of step to this, or rule, is you determine the number of valence electrons associated with each atom in the compound. So you are going to determine how many valence electrons everything has, and then you're going to add them up. If we're dealing with an ion, like a polyatomic ion, you're going to subtract one electron if it's a cation. If it's a positive ion, you'll subtract one electron for every positive charge. So if it's a +2, you'll subtract 2. If it's a +3, you'll subtract 3. If it's a polyatomic anion, that means that it's negative, so you're going to add an electron. So you would then put it in brackets and then put the charge on the outside of those brackets for or you would have the charge outside the brackets, and then you would add an electron for every negative charge. I'll show you some examples of those here in just a little bit. So then the third thing you're going to do is connect the central atom to each of the surrounding atoms with single bonds, which it should already be set up that way because that's kind of your skeletal structure. So now your job is to complete the octets for all of the atoms bonded to that central atom. So we're going to start off by just making sure that everything gets full. That's our goal, is to get them to that full octet of 8 electrons. Hydrogen, remember, only needs to have 2. All the other ones need 8. Any electrons that are not involved in bonding are going to be represented as lone pairs. So we would call them the non-bonding electrons. They would be the lone pairs on the outsides. And then after the terminal atoms, so we're going to start with the atoms on the outside. After all of them have an octet, then we go and fill the central atom with whatever valence electrons are still available. If there's number 5 is if there's not enough valence electrons to give that central atom an octet, we're going to move the lone pair electrons from the terminal atoms to form a new bond. So this is where you end up with like double bonds or triple bonds, and you just keep shifting those electrons until everything has 8 surrounding it. And then in the end, you just recheck to make sure that everything has 8 and hydrogen has 2, and you've accounted for all the valence electrons. So those are the steps. For the rest of this, I'm going to take you guys through an example. So to actually show you how the steps work. So we're going to deal with carbon dioxide, so CO2. Our first step is draw a skeletal structure of the molecule, and remember, we're going to arrange them in the order of their electronegativity. Oxygen's electronegativity is 3.5, carbon's is 2.5. So carbon's going to be the one that goes in the center. So this one is going to be the correct skeletal structure for it, instead of this one. So now that we have the skeletal structure, we need to figure out the total number of valence electrons. So we'll find the total number for that whole compound. We have one atom of carbon. Each carbon has 4 valence electrons, and we have 2 oxygens, and each oxygen has 6. So we have a total of 4 valence electrons from the carbon, 12 valence electrons from the oxygen. If you add those up, you get 16 electrons to play with. So we have got now in step number 3, we have got the oxygen bonded to carbon and this oxygen bonded to carbon. This bond here counts as 2 electrons. This is 2 electrons that they are sharing, that this carbon is sharing with that oxygen and this carbon is sharing with that oxygen. So since they are sharing already, when we go to do our counts to fill in the octet, we already have two of the electrons used up. So now let's place the electrons around the atom. So we're going to start with the oxygens on the outside. So oxygen already has 2 right here, so we just need 6 more. So we put the 6 around that oxygen. And then this oxygen has 2 right here also, so we would just fill it in with the rest of the 6. If you look at this, that gives us 8 around oxygen and 8 around this oxygen, so they're both satisfied. But the carbon only has 4 around it. It has these 2 from this bond and these 2 from this bond. So carbon is actually missing 4 valence electrons. So that's why I say this satisfies the rule for the oxygen atoms, but not for carbon. So we're not done. We're going to have to do that kind of step 5 of rearranging. So what we can do is we can just redistribute the electrons. So we can take 2 of the electrons from this oxygen and make another bond in between the oxygen and carbon. So now they're sharing 2 sets of electrons instead of 1. And we can take 2 valence electrons from this side, and we can also have them share. So now, if you count oxygen, it still has 1, 2, 3, 4, 5, 6, 7, 8. This oxygen still has 8, but carbon is now satisfied. Carbon now has 8 valence electrons around it. So the octet rule becomes satisfied, and this is the most probable structure. 4 of the valence electrons are between the carbon and the oxygen being shared. So instead of a single bond, we make a double bond. So we went back, we double checked it, we did step 6, we're good to go. If we were doing an ion, so you would do the same thing. We're going to follow the same rules, but we're going to do this for an anion. So this is a polyatomic anion, carbonate, CO3 with a 2- charge. So we're going to draw a skeletal structure of the molecule. Carbon is less electronegative, so we're going to put carbon in the middle, and then we're going to have the oxygens bonding around it. And you see how we put this in brackets, to show that it is a polyatomic ion. So this is not a compound. And then we put a 2- charge on the outside. So now we're going to find the total number of valence electrons. I have 1 carbon with 4 valence electrons. I have 3 oxygens with 6 valence electrons. So that gives me 18 plus 4. But because this has a 2- charge, that means it has 2 extra valence electrons. So I'm going to have to add in the 2 extra electrons. So now I have 24 electrons to work with for this anion. So when I start filling them in, I'm going to fill them in by doing the oxygens first. And if I do that, I get this oxygen full, this oxygen full, this oxygen full. And with a 2- charge, all of this has to equal to 24. And everything has to have 8 around it. So here I have 8. Oxygen has 8. This oxygen has 8. So that gives me 21. This carbon has still missing a spot, and I got to get to 24. So this carbon is still missing 2 valence electrons. So what I'm going to have to do here, so distributing the electrons around the central atom, 4 bonds, and around the surrounding oxygen atoms, attempting to satisfy the octet rule results in this particular structure. This satisfies the octet rule for the 3 oxygen, but not for the carbon. So I have 24 electrons here that I've already used up, but I don't have any more to put in this spot. So I'm going to move a lone pair from one of the oxygen atoms to form another bond with carbon. The cool thing is about this particular molecule is I could take a lone pair of oxygens from here. I could take a lone pair of oxygens or a lone pair of electrons from here or a lone pair of electrons from here. It doesn't matter which one I take the lone pair from, but I'm going to form the double bond between the carbon and the oxygen. And then you can see I still have 8 around this one. I have 8 around this one. I have 8 around this one. And now I have 4 around carbon. And all of that is going to equal 24 electrons, still with a 2- charge. So it gives me just a little bit more flexibility in my structure that I create. So what I want you to do is try to practice these. Come to class tomorrow with trying to practice these. We are going to go through these 5 examples in class. So I'm going to skip through this because this is the one that we'll spend most of our time with in class tomorrow. So just a little bit more about Lewis structure stability, multiple bonds, and some bond energy information. So you saw in there that there's single bonds. That means that 1 pair of electrons is shared. A double bond, 2 pairs of electrons are shared. And then a triple bond would be 3 pairs of electrons are going to be shared. In terms of stability, a triple bond is incredibly stable compared to a single bond. So stability increases with the number of electrons they're sharing. So the bond energy is the same way. So the amount of energy required to break a bond holding 2 atoms together. You are going to have to put a lot of energy into breaking a triple bond versus breaking a single bond. So, and the bond length, you can think about it in terms of like the distance between those 2 atoms that are sharing those electrons. In a single bond, they're further apart. The more electrons they share, the closer they get together. So we can draw this in class to give you an example to show that these are going to be closer together, but they're going to have more energy with them and they're stronger. A triple bond is. So, you might notice, like I said, that the Lewis structure for carbonate, if you all were to draw it, it could look 3 different ways. You could put the double bond in 3 different locations. And it wouldn't matter if you had it with the double bond of the oxygen coming off the top, the double bond on the right, the double bond on the left. It doesn't matter. All 3 of these structures equally exist and don't equally exist. So experimental evidence shows that all bonds are the same length, meaning there's not really a double bond in this ion because all of them are, it's actually existing as a hybrid of all 3 of these. So none of these 3 Lewis structures actually exist, but the actual structure is the average or hybrid of these 3 Lewis structures, and we call this resonance. So 2 or more Lewis structures that contribute to the real structure. And in this case, you can draw 3 different ones and they would all 3 be correct. So if you can draw it in multiple different ways, that's when you get resonance. Okay, so there are some kind of exceptions to the octet rule that we will go over because you'll see these occasionally. The first one is an incomplete octet where you have less than 8 electrons around an atom other than hydrogen. Remember, hydrogen is only supposed to have 2. So if you have, like for example, BeH2, so I have a beryllium atom with 2 valence electrons and I have 2 hydrogens with 1 valence electron each, that gives me 4 valence electrons to play with. So the hydrogen is going to have 2, that hydrogen is going to have 2, so there's my 1, 2, 3, 4 valence electrons already. That means that beryllium is not full, and that's just how it would exist. There could be an odd number of electrons, so if there's an odd number of valence electrons, it's not possible to give every atom 8. So if you look at nitrogen monoxide, NO, it's impossible to pair all of the electrons as the compound contains an odd number of valence electrons. So if you go through the process of calculating the number of valence electrons, you'll see that you end up essentially with 1 short because nitrogen has 5, so you end up with an odd number. So it can't be full. Another one would be the expanded octet. We see this with elements that are in the 3rd period on the periodic table and below. So anything kind of in that, starting with sodium, we might see multiple things bonded to, or more than 4 things bonded to that central atom. And when you see more than 4 bonded to it, obviously now phosphorus has more than the octet. It has more than 8 around it, but that's okay. That's where this is just kind of violating our kind of arbitrary rules that we've come up with, but you can still draw the Lewis structure for it. You just go ahead and draw it as 5 around it. So these are the ones that you're going to see in like the 3rd column and below. So you notice there's 40 electrons to work with. We still distribute the electrons starting with the fluorine going around, so we make sure fluorine is full. And if you do the full count around all of this, you have 8 times 5, which is 40. So we've taken care of all the electrons. Phosphorus just has 2 extra ones on there. So the goal for the next stuff is going to be to now relate to the actual geometry, the geometric structure that these form. You got to see a little bit of it here, and that's our